as usual. All right. So now, yeah. So were there any other overarching doubts, from last class, which people want cleared before we start off on more problems on the simple harmonic oscillator? Are there any doubts? Because if they are, we'll get them clarified and then move on. Any doubts, please? So this is something which I felt that, I should have explained a little better. I didn't. So I just thought that I should tell you that, you can definitely calculate the expectation value for the simple harmonic oscillator exactly the way you did for the infinitely deep well. All right. There is no difference and you will get the same answers. Ladder operators just make our life simpler. Okay, so if there are no doubts, let me just share screen with you. And the first thing I will do is I will just essentially point out once again the problems that we were doing. Okay, I will share this file with you. Don't know whether I have, send it on to the website. I know I uploaded the class and the class notes and perhaps the assignment for you, but I'm not sure I put these set of problems up. Okay, so I think the last problem we discussed last time was not about the one-dimensional harmonic oscillator, but actually about the three-dimensional harmonic oscillator. And this is a special three-dimensional harmonic oscillator. It's isotropic. And what that takes to mean is that your spring constant in all the three directions are the same. And last time we figured out what would be the degeneracy of the first excited state. The ground state, please remember, in most systems is unique. Okay. I mean, in fact, I cannot recall a single system where there is not a unique ground state. Okay. So the ground state is pretty much unique. It's only when you get to extremely complex systems, all right, that you could have non-unique, I think, ground states. All right. But in the systems that you encounter, the ground state is definitely unique. All right. Now let us just go on to the next problem. All right. The fourth problem, which I have put up over here. And actually, I have kind of done a bit of cheating by putting this problem in simple harmonic oscillator. Okay. So it wouldn't have been that easy to identify this as a simple harmonic oscillator problem. It was if it was just lying amongst a group of other huge number of other problems. But I just put it here to point out something to you. All right. So what does it say over here? So I'm reading out the fourth problem now. The eigenfunction for the Hamiltonian of a particle of mass m in one-dimensional potential Vx is given to be psi x is equal to a e to the power of minus bx square by 2, where a and b are constants. It follows that, and basically now you have been given four choices which ask you about the form of the potential. Okay, so the first is, of course, that the potential is a constant. The second one is the potential goes as x cube. Next one is potential goes as x square. The next one, potential goes as 1 by x. All right. Now, what you have to do is, of course, from the form of the wave function, be able to identify which kind of a potential is likely to produce such a wave function. All right. Now, as you can see over here, the wave function, it doesn't matter what A is, it doesn't matter what B is. It has an e to the power of minus x square by 2. All right. I think they should have put A and B as positive constants. Okay, that's a missing part. I think this problem is a bit ambiguous, and if somebody put it out in a competitive exam, they'd get into a bit of trouble. They have to say that they are positive constants. So now the point is that if you have an e to the power of minus x square by 2, what you have to realize is this is essentially the form of a Gaussian wave function. And if you have a Gaussian wave function, all right, then the potential is going to be a harmonic potential. And the harmonic potential goes as x square. Okay. So the answer is actually C. Vx is equal to x, goes as x square. But please note, you should keep this in mind as a kind of a problem where you could be given the form of the potential and asked to identify what is the wave function. Sorry, what is given the form of the wave function and asked to identify what is the form of the potential. All right. And there are certain very standard lengths. So for instance, we know that Vx cannot be a constant, because if it were a constant, then you would have the form of the, what do you call it? You should have the form of the plane waves, correct? The free particle. Over here, you know that it is x square and it goes, you get the Gaussian. Can anybody tell me what would 1 by x like is likely to be? I mean, I just kind of am looking at it. Any suggestions about what 1 by x could be like? Any thoughts at all? You have a potential going as 1 by x. Any thoughts at all? What could be a wave
Spherical wave function.
Sorry? I didn't get you. Could you just repeat that?
Spherical wave function.
It's a spherical wave function. Yes,
Spherical wave function.
it that is correct. It would be. So for instance, your hydrogen atom, okay? Your hydrogen atom, all right? Uh, Perhaps, you would have a little bit of trouble doing it for beyond the ground state, but nonetheless, yes, the ground state is a spherical, has a spherical symmetry. So 1 by x could look like your hydrogen atom ground state. Okay, so just think about what is the form of that. It is e to the power of minus r by a kind of a form, right? So these standard things you have to keep in mind. Of course, we haven't yet come to the hydrogen atom, so this is a slightly unfair question to ask, because I'm jogging your memory of what first semester, right? Little unfair, but nonetheless. Okay, fine. So this is the, I think 3 and 4 are fairly easily done kind of problem, so don't worry too much about it. What we will do now is we will try and, so let me just have a look at, okay, I will just stop the share and see whether I have written anything more in the place where I will send these things to you. Okay, so don't worry, please. All right, let me see, where is my other, why is it that I don't get my all the files to share? Okay, let me see if this works. Oh no, that's even worse. Can't figure out. All right. Just 1 second, please. I will just go here, open this out, come back here to Zoom. Yeah. And then let me see if I have that guy. I still don't have it. Oh, this is idiotic. Okay, no, I have it. But then I think I've lost the other file. So annoying. Right, so let me just see whether I have that worked out somewhere. Yeah. Yeah, I think I've just put it down very briefly. But frankly, I mean, this is not a very well constructed question if I think about it, okay? It's not really a good question, all right? So 1 second, please. I think I've lost that particular file again. I don't know what is happening. Yeah. So hopefully now we'll be able to get this file. Yeah. Seems to be toggling between the two PDFs. All right, so let's have a look at the fifth problem. Okay, so the fifth problem is an interesting problem. It basically says that if a simple harmonic, so I'll just take it up to the top and you can have a look at it. Okay, so if a simple harmonic oscillator, okay, 1 second, please. Yeah. If a simple harmonic oscillator is in its normal state, then the probability of finding the particle outside the classical limits is approximately. Okay, so we did talk about this vaguely, but let us just have a look at what this problem is talking about. Okay, so now you have a simple harmonic oscillator, all right, and you are told that it is in its normal state. Now, what do you mean by normal state? You mean that it is in its ground state. Okay, so this normal state here, I mean, it refers to the ground state. So if you see the normal term normal state, don't get rattled, assume it to be the ground state and move on. Okay, what they are asking you is what is the probability of finding the particle outside the classical limit, and then you have been given several percentages, okay, of finding the particle outside its classical limit. All right, Now we have to figure out what exactly we mean by classical limit, and and then try to calculate what is this percentage. Okay, so let me just stop this share. I hope you will remember this problem per se, and I will just start sharing my iScribe with you. All right, and let us just have a look at the situation. Now the thing is that when you have a harmonic oscillator, okay, so this is harmonic oscillator, and I'm talking about a harmonic oscillator. Is it visible? Okay, harmonic oscillator, this is the quantum mechanical one, right? And you know that we did do a discussion the other day, and we realized that the classical harmonic oscillator is a particular way. The quantum mechanical harmonic oscillator, ground state, and the classical harmonic oscillator, the way it looks, okay, the probability distribution, they're completely at odds with each other. The probability of finding the particle is maximum at the equilibrium for the quantum mechanical harmonic oscillator, whereas for the classical oscillator, we realize that it is at the at the extremum positions that the probability of finding it is maximum. All right. Now, what is the range of x? Can anybody tell me what is the range of x for, what positions can you find it at? Okay, for a quantum mechanical harmonic oscillator. Any So what would you be integrating over is what is important. So can somebody just tell me? So what is the range of x? Guys, wake up. I can't.
Generally, we do it from. I mean, you have not specified any limits as.
No, I haven't.
But
so what would be the range? Yeah.
Then minus infinity to plus infinity.
Absolutely. Okay. So harmonic oscillator, remember, quantum mechanical harmonic oscillator is minus infinity to plus infinity. Okay. Absolutely right. I can understand your hesitation because we just came away from the infinitely deep well and we know that is the range of the well. But here, believe me, the range is from minus infinity to plus infinity. There's nothing that is changing. All right. Okay. What about your classical harmonic oscillator? Classical harmonic oscillator, what is the range of position?
Minus extreme amplitude to plus extreme amplitude.
Okay, so let's assume that the amplitude is A. Okay, let's call it this the amplitude. So we know that it can go from plus A to minus A, or minus A to plus A, whatever way you want. Okay, so already you see that there is a difference in the range of positions for the system. All right. So in the case of the simple harmonic oscillator, no matter which state you're sitting in, it can actually go from minus infinity to plus infinity. Okay, there's a finite probability, you would say, of finding it somewhere in this range. Whereas in the case of the classical harmonic oscillator, you have this definition of extremum positions, and you will not find the system outside with a position outside of the extremum positions. That's the definition of the extremum position. Okay, now classically, how do you define the extremum position? Can anybody tell me? How is the extremum position defined?
That is the point where velocity becomes zero.
Yes, velocity becomes zero. Is there another way you can put it in terms of energies? That would help me.
Where kinetic energy is zero or potential is.
Kinetic energy is zero, yes. And so can I say that the full energy becomes the potential energy? Would it be a good way of saying it? Yes?
Yes, ma'am.
Yeah, so basically we know that total energy is nothing but kinetic energy plus potential energy. So here I say that the full energy has become the potential energy, in which case I have reached an extremum position. I hope everybody agrees with me. Okay. So now let us therefore, first of all, figure out what would be, now let's, using this definition, that when total energy becomes equal to the potential energy, I have reached an extremum position. This is the classical definition. Apply it in the case of the quantum mechanical harmonic oscillator, right? Then find out what is the probability of finding the quantum mechanical oscillator between those two limits. Okay, so now I have a plus a and a minus a. Let me find out what is the probability of finding the system between this plus a and minus a. 1 minus that should give me the probability of finding it outside the classical limits. Okay, don't worry, I said it in words. I'm going to now work it out. So just give me a minute, please. Okay, I somehow seem to have lost the problem. Just give me a minute, please. I have the whole thing worked out. I think it's there in the notes also, but it's not going to be too nice if I just do it by the notes. I know that, yeah. Okay, I need not look at it, but nonetheless. Okay, so basically, okay, as I said, we define your extremum position. Okay, so extremum position can be defined as position where total energy is equal to potential energy. Okay, so classically, you know that there is no more kinetic energy. All right, so velocity is 0, and then the particle cannot progress in the same direction. Okay, right. So now let us think about how do we write potential energy in the quantum mechanical respect. So you write it as half m omega square x square, right? Am I right? Yeah. So this is how we write it. And of course, your total energy, we'll write it as E. Now, given this, okay, given this equation, let's equate them. We should be able to find out what is x. So this implies I'm going to bring the x square onto this side is going to be 2e by m omega square, right? Which implies that x is going to be plus or minus 2e by m omega square under root. Correct? Yeah. So this is basically what we have. Now, what have we been told? We have been told that the harmonic oscillator is in its ground state. Okay, the ground state, they didn't put it as ground state, they put it as normal state. Okay, right? So then what is E over here, please? If it is in the ground state, what is the total energy?
Half h cross omega.
H cross omega by 2. Correct? So what we do now is we thereby calculate your x, which is going to be plus or minus 2, and then your E is going to be h cross omega by 2 by m omega square power half, which is going to be plus or minus, and then your 2 and 2 cancel, and then you'll have 1 omega go away. So you have h cross by m omega, h cross by m omega power half. Okay. Now, if you remember, when you had written down the wave function of the harmonic oscillator, okay, so let me just put it down once again. All right. Essentially, okay, so this is just recall, all right. I mean, I'm just justifying the symbol that I'm going to put, but you can just go ahead and do it with this. Okay, it doesn't matter. So recall that your psi nx, okay, was equal to you had essentially 1 alpha divided by root pi 2 to the power of n factorial, the whole thing to the power of half. Okay, then e to the power of minus alpha square x square by 2. Okay, and then you had, of course, your Hermite polynomial alpha x. Okay, so this was essentially how it is. Question is, what was this alpha? If you actually wrote down this alpha, you would find this is nothing but m omega by h cross to the power of half. Okay, I think I did give this to you last time, but what I would like to point out is this is nothing but plus or minus 1 upon alpha. All right. Okay, so we will just use this 1 upon alpha instead of putting that whole h cross by m omega to the power of half. Okay, so that is why I'm just justifying, but you need not. See, if I just written 1 by alpha, you would be thinking, why is ma'am putting 1 by alpha? Why not just alpha? That's because the alpha has another significance. Okay, yeah, in terms of the wave function of the harmonic oscillator. So that's the only reason. Okay, so now what are we supposed to do? Okay, let's find out. So I'm going to change the page because, oh, yeah, I'll change the page because I'll very soon run out of place here, and then I will be going on to the next page and then getting confused because I don't know how to follow it up. All right. So now let us look at what is the probability we need to find out. Okay. So we need the probability of finding the particle outside classical limits, right? So the way, so suppose now this probability is essentially P. Okay. So what should this P be equal to? It should be equal to 1 minus probability of finding particle within classical limits. Correct? And how do we find this? This definitely is going to be the integral, okay, of minus 1 upon alpha to plus 1 upon alpha, okay, which are the extremum position. And then what do we do? Mod psi x square dx. Okay. So essentially, our problem now boils down to figuring out what this guy is. All right. So now let's write it down. Okay. And please note what I'm going to do is I'm going to, go for the bare minimum. All right. I'm not going to write down the whole ugliness of the wave function. I'm just going to write down the bare minimum. So thereby our probability P must be equal to 1 minus integral. So we have now from essentially, yeah, let me just write it down, minus 1 upon alpha to plus 1 upon alpha. Okay, and then we have essentially your, okay, I have written it as alpha by root pi. Okay, I will just retain it. There are some other constants. I'm not going to bother too much. So there'll be a square, of course. And then you'll have an e to the power of minus alpha square x square. Okay, there's a by 2 which will go away. And then, of course, dx. Okay, so this is the integral that we need to find out. And let me just write it down again. This is your alpha by root pi. And then you have is minus 1 by alpha plus 1 by alpha, and then we have e to the power of minus alpha square x square dx. Okay, so this is basically the integration that we need to find out. Now, what this boils down to again is essentially figuring out this particular integral. Okay, so what I'm going to do now is I'm going to take a little effort and show you how to do this integral. All right, because it's a trick that you can probably pull off in other places. All right. So you may, of course, just memorize the answer, know it from a standard integral. But I think it's a little good to know the trick of doing this integral, simply because, again, it's something that may help you in other places. So let's have a look at how do we go about doing this integral. So this integral, okay, which is nothing but uh, minus 1 upon alpha plus 1 upon alpha. You have e to the power of minus alpha square x square dx, can be written as, okay, so I'm going to now do a double integral. Okay, you might be thinking that I'm actually making my life a little tougher, but as I said, this is a trick. Okay, and it may make your life easier elsewhere. All right, for all I know, I think maybe Usha ma'am has already taught you this trick. Okay, dx dy half. Okay, so basically I'm trying to use the fact that it's perfectly symmetrical, whether it's in X or in Y, and then I go ahead and do it. Now, what it helps me do is actually it helps me, make my limits rather nicer. Okay, so let's see what it does. So let's put your alpha x as equal to some x prime, right? Which of course implies that your alpha dx is equal to dx prime, which implies that your dx, sorry, is going to be essentially dx prime by alpha, right? Also remember, when x is equal to 1 by alpha, your x prime will be equal to minus 1. And similarly, when x is equal to minus 1 by alpha, your x prime will be, it will imply that your x prime will be equal to plus 1. No, I did it the wrong way, right? Yeah, what's wrong with me? This should be plus 1, this is minus 1. Okay, sorry guys, all right? Let me write down the plus properly. Okay, that was my mistake. Now, similarly, of course, your alpha y, you can put it as some y prime. This implies that alpha dy is equal to dy prime, which implies that your dy is equal to dy prime by alpha. And similarly, when y is equal to 1 by alpha, y prime will be equal to 1. When y is equal to minus 1 by alpha, your y prime will be equal to minus 1. So now your I, okay, becomes essentially equal to, let's not forget you have 1 upon alpha square, you have a double integral from minus 1 to plus 1, minus 1 to plus 1, and then you have e to the power of, and here I will write it as minus x prime square plus y prime square. All right, and then you have dx prime dy prime to the power of half. Okay, so this is what you get. All right, now what you do is you take it another step further. All right, so let me just again, as I told you, you can always do it by remembering a standard integral. But if you're like me, okay, who has a pathetic memory, I don't think so. I think everybody has a better memory than I do. Okay, so if you have a pathetic memory, it will be nice to remember how to solve this integral. Okay, so now what do? We introduced another, okay, this x prime plus y prime, let's put it equal to some r square. Okay, and we are now going to work in some polar coordinates. So you polar coordinates of r theta. Remember that x prime is equal to r cos theta, and your y prime is equal to r sine theta. Okay, and of course your dx prime dy prime will become r dr d theta, right? Okay, now here there is one issue which is about the limits. Okay, what are the limits? You are defining this, but please remember, because there is also this, the limits of r. Okay, so limits of r are going to be, r will go from 0, okay, yeah, and it will essentially go till r is equal to 1, simply because of this, okay. R is like the magnitude and x prime and y prime are like the components, okay, and we know that there is this relation r cos theta, r sin theta for x and y. So when x becomes maximum, x prime becomes maximum, y prime will be minimum. When y prime is maximum, x prime will be minimum. So together you will always get a limit of 1, upper limit of 1 for r. All right, so it's basically what you have defined a what do you call it, um, circle in some sense, okay, for the whole thing. Now what about the limits of theta? That is of course from 0 all the way to 2 pi, okay. This is the limits of theta. So now let's again look at the integral. The integral will now be, okay, so I'm going to take out the 1 by alpha out of that square root sign, and then we will have an integral 0 to 2 pi of d theta, okay, nothing else depends on that. And then we'll have 0 to 1 of e to the power of minus r square r dr, okay, to the power of half. So this is going to be equal to 1 by alpha. You'll have over here 2 pi, correct? And then you'll have 0 to 1. Oh, why am I writing the whole thing again? Anyway, it doesn't matter. Okay. So now again, another substitution. I have to do it this way. I'm sorry. Okay. So your r square can be equal to u, which implies that 2r dr is equal to du, okay, which implies that of course your r dr is going to be du by 2. Also when r is equal to 0, it implies that u is equal to 0. When r is equal to 1, it implies that u is equal to r square is equal to 1. So your limits actually are not changing. So therefore your I becomes now equal to 1 by alpha 2 pi 0 to 1 e to the power of minus u du by 2 to the power of half. This is a fairly easy one to do. So we will get root 2 pi by alpha outside, and here you will get integral 0 to 1 e to the power of minus u du to the power of half, so which is equal to root of pi by alpha, and then you get minus e to the power of minus u to the power of half. So now let's find out what is going to be our probability. Your p was going to be equal to minus 1, this I quantity, right? No, sorry, I think for the I have to add in some more, one constant I have missed out, right? Just 1 second. How did I define the I? Yeah, this I, yeah, I have an alpha by root pi here, right? And then I have called this I. So it's 1 minus alpha by root pi into I. Yeah, so I shouldn't forget that, right? So you have alpha by root pi into I, which is equal to 1 minus alpha by root pi into root pi by alpha. And then you have your minus e to the power of minus u, okay, and you will basically do this. This will be of course to the power of half, am I right? Yeah, and sorry, this has to be between 0 and 1. This also has to be between 0 and 1. All right, so now when I do this, of course this and this cancel off nicely. All right, I have 1 minus, and then I have over here, I will end up getting 1 minus e to the power of minus 1, okay, power half. All right, so yeah, so this should be essentially my probability. Now, just if you have your calculator somewhere around you, just see what what will you get. Okay, you know the percentages that you have got over there. All right. So let me, I hope everybody has got it to this point. So now it's just a question of numerically evaluating this and converting it into a percentage, right? So let me just get back to that question. All right. So I'll stop this share. So everybody remembers this, right? 1 minus 1 upon e to the power of square root, right? So that is what we need to evaluate. And let me just share the question, which I have lost again. Why? Yeah, no, this is the one. Thank God. Right. Yeah. So you can see what are the percentages which are given. Okay, 16%, 24%, 48%, and 84%. Now the chances are, okay, if you were in a competitive exam and you didn't have much time to do the, this integral calculation, what you have to realize that it has to be, it cannot be hugely outside the classical limits, right? So it has to be either 16% or 24%. So you can happily eliminate C and D. But in between these, okay, people have told me, and I haven't done the calculation, I should have, but the point is I haven't put the numerical value. I've obviously done the calculation, but people have told me that depending on what they take for E, how many decimal places, it can be between 16% and 24%. Okay, the choice is up. So can anybody just quickly do this calculation and tell me what they get? Anybody who has their calculator around? I don't know where I have mine. Maybe it's here. Okay, let me also give it a shot. Just give it a shot and see what you're getting, and maybe we can.
20.49%, ma'am.
How much? 20 point. Can you put it in the chat box?
49.
I can't hear you, Nitin.
Yes, ma'am.
20.49, ma'am.
20.49, is it?
Yes, ma'am.
Okay, so then neither works, all right? But essentially it is either A, it's between A and B, okay? So then it's a toss up. I mean, this is sounding like it is something right in the middle, all right? But nonetheless, let's forget about the multiple choice question and, choices given here. But this is the way to do the problem, okay? And what you realize is, so identifying something like what is a classical limit, and then figuring out what would be the probability of finding something outside the classical limit. Now, this is an interesting concept per se, that in the classical harmonic oscillator, the probability of finding the particle outside the classical limit is zero, basically. There is no argument about that. Not so for the quantum mechanical oscillator. Of course, in the quantum mechanical oscillator, please remember your whole definition of putting the classical limit is a classical concept. Okay, it's not really a quantum mechanical concept. So thereby there is a finite probability of finding the system outside the classical limits. All right, now let's just have a look at the sixth problem. I'm not going to solve the sixth problem, but let us just look at it and see how we are going to approach it. What does it say over here? Find the probability of finding the particle outside classical limits given that the harmonic oscillator is in its first excited state. So can anybody amongst you tell me how would you approach this problem? What would be the way of solving this? Any ideas? You saw how we solved this particular problem when the system was in the ground state. How about when the first excited state?
Same
Yes,
way
Jay.
we use psi1 instead of psi0.
Yes. Apart from that, what else? There is another very important parameter. You have to use psi1. Absolutely correct. What else?
Ladder operator acting on
No.
psi.
Let's not get into the ladder operator. How about the classical? How about the limits? See, the limits are also very important, right? How do you define the limits?
Energy, ma'am.
Correct. Total energy must be equal to potential energy, correct? What about the total energy in the first excited state? Isn't it higher? It's not h cross omega by 2, right? What is it?
3 by 2 h. 3 by
Yes.
2 h cross omega.
3 by 2 h cross omega. So now you have to define your classical limits using the total energy as 3 by 2 h cross omega. All right. That, and you have to use psi 1, right? Then go ahead and do the calculation in exactly the same way. Of course, the integral is going to be different, right? Because your psi 1 looks different from your ground state. Not very different, but nonetheless, yeah. So I would like you people to give this a shot. Okay. Give the sixth problem a shot. I will post you this list. All right. Once we have finished discussing all the problem, I'm going to post this list. So the sixth problem, I want you people to give it a shot. Do it in the manner that we discussed the fifth problem, except that you remember now that your total energy is going to be the energy of the first excited state, the first excited energy eigenstate. Sorry, said it wrong. First excited energy eigenvalue. Okay. So that is what it is going to be, which is 3 by 2 h cross omega. And you have to use psi 1, right? Okay. So now, yeah, let's move on to the next one. And this, I think, is a problem that we did solve, okay, in our perturbation theory. Okay, so nonetheless, let me just read it out to you. One-dimensional harmonic oscillator with mass m and charge q is subjected to a uniform electric field E. Estimate the energy eigenvalues of the system. So do people remember this? Okay, if we don't remember, I will show you. I have my, I think, scanned notes. I can just show you the thing. If you do remember, we will skip it. So I want a consensus from people. How many of you remember it? How many of you would prefer to, see the scanned notes to see how we do this problem? It can be solved exactly, okay? So you actually don't need to use perturbation theory here. I did that also, I think, in class, but I understand that the classes were mostly online. So would you like me to show it again, please?
Ma'am, we will try this once on our own.
Okay, which one? The seventh problem as well?
Yes, ma'am.
Wonderful. Wonderful.
I think.
Yeah. So Chetan at least thinks that he would like to try it on his own, which is a very good thing. I hope everybody else is agreeing with it because they're not saying anything. I have to say that silence gives consent. Okay. So the seventh problem, I'm again assuming that you will try on your own. In the next class when we meet, if there are issues, I will discuss it. Okay. As far as I remember, I did do this problem. Okay. Because you did second semester a lot of the quantum mechanics with me, and we did handle this in perturbation theory. Okay. All right. So if you want a clue to everybody, is that this is a perturbation to the simple harmonic oscillator, and it's a linear perturbation. Okay. The perturbation goes as X. Okay. So please look it up. You will find it. All right. Now let's go to the next problem. All right. So the next problem, what does it say? It says that you are asked the energy levels of a particle of mass m, which is moving in a one-dimensional potential of, please make note of it, this is Vx is equal to z infinity for x less than 0, and it's equal to half m omega square x square for x greater than 0. Okay. So it's not, as you can see, a symmetric potential. That's the first thing that you will note. It's not a symmetric potential. And for x greater than 0, it is actually a harmonic oscillator potential. Correct? Yeah. So I hope everybody has noticed this. And now you're being asked what is going to be the energy eigenvalues of the system. Right? So let's have a look at this. So just keep this potential in your mind. And we will now, I will just stop the share and I'll go on to my iScribe. Okay, there's some. Okay. So I see the answers that have been put 20%, 20.49%. Okay. So I don't know, I mean, like I've picked up these, what do you call, problems from somewhere. Maybe the sources were not the bestest. Okay, so which is a bit bad, I think. Yeah. Right. So let me now try and once again tell you what this potential looks like. Okay, and then let's discuss and see whether we can arrive at the solution. Okay, so your Vx is equal to 0 for x less than 0, and it is equal to half m omega square x square for x greater than or equal to 0. Okay, so this is what it is. All right, so now I think I will have to change my page. I'm sorry. Okay, I shouldn't have bothered to write it over here. I should have just gone on to the next page. You know, there is a bit of a mismatch between what you can see on the screen and what is actually the reality on my paper. See, I am bound by classical limits. Okay, so the bottom of the page of mine is different from the virtual page which you are seeing. So when it looks like there's space at the bottom, there's actually none over here. All right. So okay, so let's now have a look at this particular uh, v of x. Okay, so let me not I'm trying to locate where I have done the, so it's infinity for x less than 0. It is equal to half m omega square x square for x greater than or equal to 0. So now what does this actually mean if you just think about it? Let's just draw the x-axis. This is your x-axis, this is your 0, this is your v of x. And what is happening at x is equal to 0, it is going off to infinity, right? Your potential, which means essentially that this entire area is inaccessible to the system, right? So your wave function is bound to go to 0, okay, for region x less than 0. What about here? It is essentially your standard half m omega square x square potential. Okay, so it is a parabolic potential in the positive side. So now how do we go about solving it? So can anybody, you know, I had kind of taken a little bit of pains and told you about the wave function of the linear of the harmonic oscillator and how it changes for the different excited states. Now can people tell me about the positions of the nodes? Okay, you remember I had been harping about the nodes. So does anybody have any memory of that? Meantime, I'll try and locate where I have actually done this solution. Yeah, I think I've kind of found it. Any memory, please? Okay, so let's have a look at the normal harmonic oscillator. All right. So what do you have over here? You have essentially, this is your x is equal to 0. And this is, I mean, I will just say this is energy or it is v of x. Okay. Yeah. So your thing is a parabola, right? Okay, hopefully I managed to do it a bit. And then you have, of course, your first energy state is sitting at half h cross omega. And then, of course, we have double of this and then triple. And then this is your first excited state. This is 3 by 2 h cross omega. And then you have this and this. Yeah. And this is your 5 by 2 h cross omega. Okay. And then again, so on and so forth. Okay. 7 by 2 h cross omega. So if you remember, your probability distribution for the ground state was something like this, right? Symmetric with the highest potential at the center. What was it for the, this is how it looked for the first excited state. Second, for the second excited state, it was something like this, right? For the next excited state, that is the third excited state, it was essentially something like Okay, and I hope you remember this. Okay, so what have I plotted here? Please note, apart from these two energies, I'm also plotting what is the probability of finding the system at a particular x. Okay, so now can you just tell me? So this is, please note, for n is equal to 0, this is n is equal to 1, this is n is equal to 2, this is n is equal to 3, and so on and so forth. Now, can anybody tell me where are the nodes, okay, for the various excited states? So there is a general observation that you can make, and I had made this observation for you guys, okay? But can you just check it out now and tell me where are the nodes, okay? Does it depend upon the n value?
There will be n nodes for any given
Correct,
nth state.
correct. And what about the position of the node? See, for instance, let's have a look at the ground state. Okay. Obviously, there are no nodes, correct? And
Yes.
yeah. Now, in the case of the first excited state, there is one node and it's located at the equilibrium position, correct? In the case of the n is equal to 2, there are two nodes, but the nodes are located on either side of the equilibrium position, not at the equilibrium position. Okay. Go to n is equal to 3 and you will find that there are how many? Three nodes. Yeah, there are three nodes and one of them is at the equilibrium position. Now, go back to our problem, please. Okay. And what you realize is that for x less than 0, okay, your potential goes to infinity. What does it mean will happen to the wave function? What will be the wave function for s less than 0? X less
0.
than, sorry?
0.
It has to be 0. Okay. So for continuity purposes, at x is equal to 0, what will have to be your wave function?
Continuous.
Yeah. So it will have to be at psi 0. Okay. Yeah. Your psi 0 over here. Your psi x for x less than or equal to 0 has to be 0. Okay. So for continuity purposes, at x is equal to 0, psi x has to be 0, which means your px is also 0. And what you can see over here, okay, is that there are only certain states that are going to satisfy it. So which are these? Which states are going to satisfy your psi x equal to 0?
Odd states.
Yeah,
Odd
exactly. At
states.
x is equal to 0 and px is equal to 0 at x is equal to 0. At odd states. Absolutely correct. Okay, so this guy satisfies, this guy satisfies. All right. Whereas, so what is going to happen is by creating a wall. So please note, you have a harmonic potential for positive x, but you've created a wall, an infinitely deep potential. Okay, in some sense, below x is equal to 0. So the wave function has to go to 0 at x is equal to 0, which you will realize is only possible for your odd states. Okay. So thereby your energy eigenstates of this system, okay, will essentially be you have to take the simple harmonic oscillator solution, but you can only take odd n. All right. So let us now see how that looks in for a normal simple harmonic oscillator. This n should be equal to what? N plus half h cross omega, right? And here, what will it be? Instead of n, we have to make it odd n, right? So it will be essentially, you will have 2n plus 1 plus half h cross omega, right? So it will become essentially 2n plus 3 by 2 h cross omega. This is what you're going to get, okay, for n is equal to, so you will start off, you put n is equal to 0, your lowest energy is going to be 3 by 2 h cross omega, which is correct. Then you put n is equal to 1, And then you will get what? You will get 4 plus 3, which is 7, 7 by 2 h cross omega, which is essentially n is equal to 3. So your En is going to be this. Okay, so please remember, okay, there was no need to actually go and do, complicated solution. All you had to remember is that, hey, now I have a wall. So my wave function goes to 0, and thereby I will only have the odd states existing. Okay, so let's just go back. I know I'm over time. Okay, so just one last this thing. I will, where are, yeah, here we are. Okay, so you can look at it, and what you will realize, okay, they haven't done it correctly again. I don't know why they have written it as 2n plus 1. I need to really change a lot of these problems, it looks like. Okay, your answer should be essentially the last one. Okay, it should not be 2n plus 1. Okay, it should be just n. All right, so En is equal to 2n plus 3 by 2 h cross omega. Okay, so your choice should be choice T. See, a lot of these problems have actually been taken from our ex-students, okay, and what they remembered the solutions to be, the multiple choices, because very often they were not allowed to walk away with the question papers. So sometimes I think when we have written it out from their memory, we have written it out wrong, okay, or they have written it out wrong and we have just carried it over. So it is essentially the last choice. Okay, I hope that kind of makes it clear. Now I will send over this question set to you so that you know what all problems have been discussed in class. And please try solving question 6 and definitely try 7. You should be able to do 7 because of the simple reason is that we have discussed this. Okay. What I would like you to do is also try and plot how the energy levels will look. All right. It will just clarify things for yourself. All right. So with that, let me stop the share, and yeah, I will stop the recording.